All right, thank you very much. So I think, can everyone hear me? So I'd just like to open, what I'm going to be talking about today is stable isotopes as tracers, but also a lot to do with the complications of using different types of tracers to look at sources and processes. So I wanted to open with this really interesting newspaper quote I found around the time of this last groundwater conference, when dairies were big in the news, saying 65% of domestic wells at Central Valley dairies test over the public health limits for nitrates, yet none of the dairies was fined for a nitrate problem identified by the state. So we have this very big disconnect, particularly in the public perception of, okay, if you have a land use and you've got a well on that land use, well, obviously whatever's in that well must be directly connected to that land use. And I think, as everyone in this room knows, that's absolutely not the case. And we have a wide range of different interrelated factors that will in fact be controlling the water quality in any given well at various different depths and in even very close locations. So we have widespread use of different types of nitrate sources. And we also have the issue of the age of contamination, or just age of geochemical indicators. What's actually getting into that water and what time frame did it come from? So I'm going to be talking about a sort of small aspect of a much larger study. So I'm going to be focusing on the USGS components in this larger study, particularly, and this is another place where I'd say sometimes even researchers are disconnected from what's actually happening, looking at, does groundwater impacted by dairy use have a distinct isotopic signature? A lot of times in both the isotope and geochemical research worlds, we'd like to say, okay, we have 3 end members, they look like this, let's do some mixing models, very simple ones, and say, okay, what proportions are coming in? We wanted to actually look very closely at what we thought were end members and see how much variability there is even in sort of our best measurements of them, and use that to look at what are the primary drivers of groundwater quality variability beneath dairies, looking at different land uses within a dairy, like lagoons, corrals, and fields, the question of source inputs versus biological and chemical processes. In different wells, is it really inputs controlling that, or is that post-input processes? We also have the question of length of time in use as a dairy, and what do regional differences, what sort of impacts did these have, particularly when we have very different depths of groundwaters? And finally, I'm just going to touch on how, in this study, how these findings relate to local drinking water quality. So as I said, this was part of a larger study. It was a collaborative study led by Thomas Harder, funded by a Prop 50 Clean Water Drinking Water Act, that had collaboration with a lot of UC Davis people, Lawrence Livermore National Laboratory, and the U.S. Geological Survey. The overarching design of this study, we were looking at 2 different regions within the Central Valley and also 2 very different well types. So we have the San Joaquin Basin region, which has a much shallower water table, considered potentially high vulnerability in terms of rapid response to land use changes. We have the Tulare Lake Basin, where we have a much deeper water table, so potentially longer response times to current land use. We had 2 very different types of well installations. We had what I'm going to call the dairy monitoring wells throughout this talk. These were dedicated sampling wells installed for the purpose of research and observation. So they were installed specifically to attempt to reach about the top of the water table. So the installations and depths were very well known. These were at 7 dairies with multiple wells, sometimes multiple depths per dairy. We had another data set of domestic supply wells. This was 200 private wells in these spread across these 2 different regions that were sampled with owner permission. So these we had much less control over exactly where the different wells were and what sort of knowledge we had about total screen depths and total depths to water. So since this is a really wide diverse audience, I want to just take a step back. I know we have everybody from isotope experts to perhaps people who are much more used to working with concentration analyses. So I just want to talk a bit about some of the weirdness we have for reporting isotope ratios and what that means. We report isotope ratios not as a total amount, but as a ratio relative to an agreed upon international standard. So we report it simply as a ratio of the heavy isotope to the light isotope in your sample relative to this standard. And we just set this international standard as 0 per mil. So this is where we get into having negative and positive numbers, which seems really weird when you're talking about something like nitrate. This doesn't mean we have less nitrate or more nitrate in any of these given wells. It simply means that the isotope ratio of the sample either had more of the light isotope compared to this international standard, so that's where you get the negative numbers, or more of the heavy isotope. And these also don't come with any sort of value judgments. You know, positive isn't good, negative isn't bad. It's simply what it is relative to this standard. Okay, it's thinking about moving. All right, so this is a fairly classic nitrate isotope source diagram. This is from some of Carol Kendall's review chapters, looking at N15 along the x-axis and O18 of nitrate along the y-axis. And these boxes show the general range over many, many, many different studies in a wide variety of areas where the different sources tend to fall in terms of isotopic signal. And what you can see here is that human and manure waste tends to be much more enriched in N15 of nitrate compared to either natural soil nitrogen or nitrate that's coming from nitrification of synthetic fertilizers. Using O18, you can often distinguish chemical in the form of nitrate fertilizers or nitrate in precipitation. One of the big complications is that processes can also shift this isotope signal away from the original source signal. Luckily, these processes, especially denitrification and groundwater, you can use both the isotopes and concentrations to find a pattern in the shift. So if denitrification occurs, let's say you start with sort of a source signal in this in-between area, this will cause a coupled increase in the N15 in a linear fashion with an increase in the O18 and also a significant reduction in the total mound of nitrate. So we can look at both the nitrate isotopic composition and concentrations to try and tease apart, are we seeing primarily a source signal or primarily a process signal in whatever water sample we're measuring. So I'm going to get to some of the data from this large study that we have. This is that same nitrate isotope graph shown with all of the data from both of the different well types across the different regions. And the big thing I want you to take away from this is that when we look at these first encounter dairy monitoring wells located on dairies, we don't see a tight cluster just in the manure and septic box. We see basically the entire range across the data set of both N15 and O18 values. So with these dedicated wells, we're already seeing a huge amount of variability. The domestic wells, so the domestic supply wells, show a bit less variability, but even there we're seeing a wide range of different isotopic compositions. So this brings us first to the question of, well, are we just simply seeing a source signal that started out the same and has really just been undergone different amounts of denitrification? Are we really just seeing only a process signal? Well, one of the ways to look at this, there we go, is to look at the N15 of nitrate value of, this is the entire data set for just the dairy monitoring wells. So I'll wait until near the end to show any more of the domestic supply well data plotted against nitrate concentration. And so here we find that rather than seeing increasing N15 of nitrate with decreasing nitrate, we see these high N15 values across a wide range of nitrate concentrations, including really elevated nitrate concentrations as well. And Lawrence Livermore's data also confirmed this lack of saturated zone denitrification. There was only one well which clearly showed its own strong denitrification signal where we found both super high N15, very low nitrate, combined with excess N2, which is a totally independent tracer of did denitrification occur within the saturated zone. However, this doesn't rule out that some denitrification is almost certainly occurring within the unsaturated zone, but not enough to significantly attenuate any of these nitrate concentrations. So like I said, there are different land uses within the dairies themselves. So a dairy isn't just one single land use. You have various things like the waste lagoons, which can possibly leak, especially older ones. We have the corral area, which may receive a lot of manure, but also have very little water infiltration. And then we have what we call, are often referred to as manured fields. However, these fields can also at different times be receiving chemical fertilizer as well, depending on timing, plant requirements, and supplies of manures can be quite difficult to use as a sole fertilizer. So looking at a single, so if we look at these in terms of the land uses, and I should say, in the areas where we have very shallow groundwater, Thomas Harder's work, has shown that you're actually taking water from a fairly narrow source area. So a fairly small range of water sources should be getting into those first encounter wells. When we look at the different land uses, again here we see the entire range of different N15 and O18 values, suggesting a very strong mix of both manure or human waste sources with these chemical fertilizer sources. So these nitrate concentrations are elevated way above anything that could be coming naturally out of just unadulterated soil nitrogen. The one type of wells that do show a distinct lower N15 cluster are the upgradient wells. So the wells on each of the dairies that were designed to look at upgradient groundwater flow almost entirely from irrigated crops. So that was the one type of well land use that showed, even though it showed a wide range of nitrate concentrations, which I'll show on the next slides, it showed all of the values shifted much more towards a predominantly fertilizer signal rather than a manure human waste isotope signal. So another way that we can look at this is each of the individual wells by land use on a single dairy. So this is a dairy in a very shallow groundwater table, and this is showing the results of quarterly isotope sampling, or quarterly nitrate concentration sampling by land use. And this is a dairy that has 3 different drinking water wells on it. You can see at least 2 of these have extremely high nitrate concentrations. And you can also see that these are relatively well mixed in terms of nitrate concentrations across the different other types of dairy land use wells. However, which you can see that sort of ties back into the newspaper article, if we've got a dairy and, oh, the drinking water has extremely high nitrate. However, if we look at the isotope values over quarterly sampling of these different wells, you can see that suddenly, despite the wide range of nitrate concentrations, all of the domestic wells and the upgradient well cluster towards these much lower N15 values, while we get the spread of N15 values all shifted higher, all suggesting a somewhat higher contribution of a manure or human waste source to those different wells, while the domestic and the upgradient wells are suggesting a much stronger influence of fertilizer nitrate. Looking at regional differences between the north with shallow groundwater and the south with the deeper groundwater, even in the deep groundwater, we still see this wide range of isotope compositions, so spread across both fertilizer and manure dominant sources. And so one of the things we're looking at is what causes these different sources, and why are we getting this huge amount of variability? And one of the answers appears to be in the combination of depth to groundwater and time in use as a dairy. And this is a bit of a complicated slide, but here we have 2 dairies that have been in use for at least over 30 years. And also, so this is depth going from land surface down, so depth to groundwater. These show a wide range of nitrate isotope values, all shifted towards values that show at least a small component of potentially manure or fertilizer sources. If we look at young dairies in deep groundwater here that have only been used in dairies for a very short period, these are all shifted towards primarily fertilizer isotope signals. But where it gets complicated is once we get into the deep groundwater with dairies that have been in long-term use as dairies, we start to get this extreme heterogeneity between different wells. Some wells will be showing a very strong manure signal. Some wells on the same dairies will be showing an almost entirely fertilizer signal. And We'll wait for the slide to change. Okay, and so just going back to wrap up the talk, looking briefly at our domestic well isotope data. These are the ones I originally showed in gray. Here we have what it appears is that when we divide them up into whether or not, and this was reported by Katie Ransom's 2013 paper and her 2016 paper that was just released last week, is that we do see these higher N15 values across both the north and the south regions, but almost all of the wells that show elevated N15 values are within a given radius, within at least 2.4 kilometers of a dairy. However, this has the N15 in the domestic wells had no strong correlations at all to nitrate concentration. So even if we found a suggestion of higher manure inputs based on the isotope levels, this had no correlation to whether that particular supply well had high nitrate or low nitrate. So to wrap up, monitoring wells, so basically our best attempt to get at an end member signal, monitoring wells within individual dairies showed a wide range of isotopic compositions and nitrate concentrations. So we have extreme variability, even in both in shallow and deep groundwater. So from a scientific standpoint, assuming a well-defined, tight end member is probably inaccurate. Source studies really need to address this variability and uncertainty. And from a regulatory or monitoring standpoint, a single monitoring well is almost certainly not going to be representative of entire groundwater conditions across an entire dairy. Even within very short distances, we see extreme differences in geochemical and isotopic compositions. The variability in the amount of manure-derived nitrate appears to be controlled at the top of the water table by a combination of the depth to groundwater and the time in land use as a dairy or as cropped irrigated fields. And finally, in domestic supply wells, the higher N15 values were found exclusively in regions that were relatively close to dairies, but within the supply wells did not show any correlation with higher nitrate concentrations. So the source of the nitrate was decoupled from what the overall nitrate concentration was. So thank you very much.
Thanks very much, Megan. Right on time. So we have a chance for a question or two. Right there. Mike Renner.
Yeah, Megan, do you find any correlations with the nitrogen isotope ratio with other indicators of wastewater, for example, chloride and some other indicator, or boron isotope?
So Katie, I will say, Katie Ransom's paper using Bayesian analysis to look at these different, did find some correlations, but also it was needed, a Bayesian sort of mixing model was used to attempt to work out some of this variability and uncertainty. There was some correlations, but absolutely none of these really tight, easy correlations that are often reported for studies where, say, you have single water sources or maybe only two very well-controlled, non-managed end members. So a lot of the other tracers did not behave in the same way, either in each different well or between different dairies.
Hi, hello.
Hi.
John? Okay, I would like to ask, did the measurement of the isotopic composition of the manure itself will help to identify the source and then to narrow the range of the isotopical value for manure? Because here you use the big boxes, which are really big. No? So you have your data of your specific livestock facility, whatever, no? That will help.
So we do have a few of the waste lagoons are tricky to measure because they are so rich that you either have to clean them up or they just don't work with the method. but we do have some sort of more pure manure end members, but what it looks like is happening in the dairies is that the manure spends different amounts of time in the waste lagoon. It may receive different irrigation water, and also just the length of time it sits on the surface as manure can have a huge effect on what its isotopic composition is. So I think really, basically what we're calling a manure end member can actually vary widely just by how that manure is managed and sort of where it's sat, what sort of water it sees, whether it's completely anoxic in a waste lagoon, whether it hasn't fully gone oxic. So yeah, you can measure just the fresh manure itself, but that's really not going to be your manure end member in terms of talking about dairy manure management. And I think that's where a lot of the complications come in.